All right, guys, today we're going to start talking about solving radical inequalities. So we've already spent a couple days going over solving radical equations, but what kind of curveballs are we going to be throwing at you guys now that we're saying that these are inequalities? Well, first let's take a look at kind of our generalized solving process, okay? It's going to be similar to what we did for solving equations, but obviously there's some additional considerations that we need to consider when it becomes an inequality. So for solving first, we're just going to go and solve the entire inequality. It's going to look exactly like what we did for solving equations. The only exception to that is instead of being equal to something, it's going to be less than something. It's going to be greater than something, less than or equal to something, greater than or equal to something. And with those inequalities, we also need to remember that if anytime you multiply or divide the entire inequality by a negative, we got to flip that inequality sign around. Okay, but first we're going to go and just solve the inequality like it's any other regular old problem. The second part we need to do, though, is something that's a little extra. We have to go and set the radicand. That is what is inside the radical or what is inside the radicals if there's more than one. But we have to set what is inside the radical, the radicand, to be greater than or equal to 0. It does not matter what the original inequality is. We have to take what's inside the radical and set it to be greater than or equal to 0. Why do we have to do that? Because what happens if there's a negative number inside the radical? Oh, things are imaginary. So this second step in our process is really just us making sure that we don't include any imaginary solutions, okay? So it's kind of like we're checking it, but we're checking it in the middle of the problem, right? Right? I know, right? So once we have gone through and solved the entire inequality and set each of the radicals, or what's inside the radicals, to be greater than or equal to 0, then we're going to have a list of possible kind of inequality solutions. We're going to want to go and graph those on a number line. I just think that makes it so much easier to determine what the actual answer is. You'll see that in a minute. Looking at that number line, we're going to see where the shading is in common. And then once we have that, we're going to go through and write it in interval notation. Okay. Remember, that's using a soft bracket if it is just less than or just greater than, or you're using a hard bracket if it's less than or equal to or less than or equal to. These hard brackets are inclusive. These soft brackets are exclusive. All right. So we're going to go through 3 example problems following this procedure to see how we can go and solve these different inequalities. So to start, we've got a simple one. The square root of x plus 2 is less than or equal to 4. We should recognize that this is a radical inequality because it has, well, a radical and an inequality, okay? So in phase 1 of the problem, okay, we're going to go through and just solve the whole rational inequality. So we're going to say the square root of x plus 2 is less than or equal to 4. How would I solve that? Well, I need to isolate the radical portion. It's already been isolated, so that's super convenient. And then I'm going to use exponents to eliminate that, because when I square a square root, those are inverse operations and they undo one another. So I end up with x plus 2 is less than or equal to 4 squared, which is 16. Subtract a 2 from each side, and I get x is less than or equal to 14. Okay, so if I pick a number that's less than or equal to 14, then I'm going to end up with something that is less than or equal to 16 inside the radical. And the square root of something that's less than 16 is definitely going to be less than or equal to 4. But is an imaginary number less than or equal to 4? I don't really know. We're comparing apples and oranges at that point. So that's why I also need to go through and consider step 2, where I take just what is inside of the radical here, this x plus 2, and I'm going to set that to always be greater than or equal to 0. It does not matter what the original inequality was. Unimportant. What is inside the radical has to be positive or at least 0. So make it positive or at least 0. So in this case, I also know that my value for x has to be greater than or equal to -2, right? Because I'd subtract 2 from each side. So all the x values that are less than or equal to 14, but also greater than or equal to -2 would be considered in my solution set. So that's where this whole number line thing comes in. So I'm just going to draw a generic looking number line, and I'm going to put those two solutions on it. I'm not going to worry about appropriately spacing or scaling it. I'm just going to say the smaller one was -2. The bigger one was 14. Okay. So I'm also going to suggest that you don't actually draw on the physical number line, draw above it. You'll see what I mean here in a second. So first off, our condition was that x is less than or equal to 14. Less than or equal to is inclusive, so I would use a solid dot, okay? Less than or equal to 14. Well, less than means to the left of, okay? So all the values to the left of it. I also happen to know that x has to be greater than or equal to -2. So I go to -2 and I say greater than or equal to, so a solid dot, okay, it's inclusive, but it's greater than. Well, what's greater than -2? All the numbers that go this way. So I can go through now and say, hey, like they're both at -2 and they're both also at 14, and everything that is the two lines, they're both true statements, is in this section right here, okay? Way over to the right, I'm not including the first inequality. Way over to the left, I'm not including the second inequality. So what is including both of them? Well, everything in between and including -2 to 14. So I can go and express my answer as x is equal to hard bracket, because I did a solid dot at -2, comma, 14, and that one will also have a hard bracket because it includes the number 14. So all the numbers in between -2 and +14 will make this a true mathematical statement. All right, let's go take a look at the second one, okay? The second one, we have an inequality where we have a radical on each side, okay? So that means we're going to have additional conditions, okay? But the first thing we need to go through and do is we just need to go and solve the whole inequality, right? So we're going to say the square root of 5x minus 16 is less than the square root of 2x minus 4. So I have one radical on each side. I can get rid of them by doing one mathematical operation by just squaring both sides, because inverse operations undo each other. So we end up with just 5x minus 16 is less than 2x minus 4. So solving this, I would subtract 2x from each side, and I would get 3x. It's still less than. I'd add 16 to each side, and I would get like 12. Dividing both sides by 3, I would get x is less than 4. Okay, so x has to be less than 4 for this to be a true statement. However, neither one of these radicals should be imaginary. Okay, so I need to set 5x minus 16 to be greater than or equal to 0, and 2x minus 4 also has to be greater than or equal to 0. I have two radicands, ergo, I have two different new little mini inequalities to go through and solve to make sure that I don't have any imaginary numbers. So I could say add 16 to each side, so 5x is greater than or equal to 16. So x is greater than or equal to 16/5, which if you wanted to go through and use a calculator and figure out exactly what that is, 16/5 is really just 3.2. Over on the other side, 2x would need to be greater than or equal to +4. So x would need to be greater than or equal to a +2. All right, so I've got three conditions here, and this is really the reason why I suggest not actually shading on the physical number line like you did in elementary and middle school. And the reason is you're going to end up with overlapping shading, and sometimes that makes it a whole lot more challenging to do, right? So I'm going to put my three numbers on there. Again, I'm not really worried about scaling it. I'm just worried about putting it in an order. So I know I have the smallest value is 2. My next largest value is 3.2, and my largest value is 4. Okay. So if I start with the smallest one, okay, x has to be greater than or equal to positive 2. So greater than or equal to means solid dot, and these are all the numbers that are greater than it. If I look over here, x also has to be greater than or equal to 3.2. So greater than or equal to, so it's inclusive. These are all the numbers that are greater than or equal to 3.2, okay? Then when I get to 4, x has to be less than 4. Not less than or equal to, just less than. So I'm going to use an open circle, and I'm going to go to the left, okay? So I had 3 conditions that have to be true in order for this inequality to work with real numbers. If I look at the section to the left of 2, only 1 condition is true. If I look in between 2 and 3.2, only those 2 conditions are true. I didn't go 3 for 3, it doesn't count. But in between 3.2 and 4, I have all 3 conditions are true. And because all 3 conditions are true, this is the section of the domain where this inequality is true and real. So if I go and write that as my solution, I would say x equals, I would need to use a hard bracket at 3.2 because I've got a solid dot, definitely included. So hard bracket, 3.2. But then I would need to use a soft bracket for 4, okay? I need to use a soft bracket because although it's included in 2 of the conditions, in this one, it's got to be less than 4. So like 3.999999999 works great. 4, 4 doesn't work. That will not make these two, that will not make this first radical less than the second radical, okay? So you see what I mean, where if we were going through and shading, it'd be a little bit harder to go through and see because you'd have, triples. So that's why my suggestion is to use the number line to create your solution that's written in interval notation, okay? If you're doing something on delta math, you may also see it written as a compound inequality. So that would be written as like 3.2, so x has to be greater than or equal to that while also being less than 4, okay? But hopefully you can see that this compound inequality looks very similar to interval notation. The smaller one is on the left, the larger one is on the right. Soft bracket means just less than. Hard bracket is the whole greater than or equal to thing. I prefer you guys going through and doing it in interval notation. That makes a lot more sense, and that's really what they end up using a lot more on like SAT, ACT questions. But just so you know, you can express it as a compound inequality. All right? So let's go through and take a look at one more, okay? So this one we have the negative square root of 5x plus 13 has got to be less than or equal to negative 2. All right. So the first thing that I need to go through and do is I need to solve the actual inequality. So I have negative square root 5x plus 13 is less than or equal to negative 2. Before I can start squaring stuff, I need to isolate it. So I'm actually going to go through and divide everything by negative 1, okay? Because I got to get rid of this guy right here. So a negative divided by a negative results in a positive, but I also need to remember that when I'm going and dividing by a negative, I have to flip around that inequality. So I'm going to end up with the square root of 5x plus 13 is now greater than or equal to a positive 2, okay? If you forget that inequality, everything in your problem moving forward is just going to be wrong. So just be careful with that. So now that I've done this, I can go and I can square both sides because I've got an isolated radical. I'm trying to use inverse operations to undo it. So we end up with a 5x plus 13 is greater than or equal to 4. So 5x is greater than or equal to negative 9. So x is greater than or equal to negative 9/5, which if you wanted to go and write that as a decimal, you would go and say that x is greater than or equal to negative 1.8. All right, but then we've got part 2, where we need to go and make sure that we're only dealing with real numbers. So what's inside the radical, that 5x plus 13, has to be greater than or equal to 0, right? So 5x has to be greater than or equal to negative 13. So x has to be greater than or equal to negative 13/5. So if you wanted to put that in a decimal form, you would say x is greater than or equal to negative 2.6. All right, so we've got our conditions determined. So let's go through and put it on a number line to help us figure out what our interval is going to be. So the more negative value here is negative 2.6. The more positive value is negative 1.8. Right? So x has to be greater than or equal to negative 1.8. So greater than or equal to implies a solid dot because it's including, and greater than. We also know that x has to be greater than or equal to negative 2.6. So greater than or equal to is to the right. So where are both of the conditions true? Well, they start being true right at negative 1.8. And when do they stop being true? Well, the answer to that is they never stop being true, because ultimately, if it's going all the way to the right, it's going towards infinity, okay? So writing this in interval notation, we could go through and say that x equals hard bracket, because it's inclusive, negative 1.8 to infinity, okay? And remember, we always use a soft bracket with infinity because it can never equal infinity, it just approaches it. All right. We could also go through and express that as an inequality by literally just writing x is greater than or equal to negative 1.8. Because if it's greater than negative 1.8, it's kind of automatically greater than negative 2.6 as well. All right. You could plug in certain numbers to go through and check that and make sure that it all worked out. But I'll go ahead and tell you that it definitely does. Okay, so the only other things that we need to discuss very briefly are some special considerations. Okay, so a couple things that we know from previous lessons that we have gone over with radicals. So we know that if it's going to be real, the square root of something cannot equal a negative. Okay, that's just not feasible within the real number plane, right? So if the square root of something can't be equal to a negative, does that imply that the square root can't be less than a negative number? Or that the square root of something can't be less than or equal to a negative number? Because if you think about it, what's less than something negative? A larger negative number. What's less than or equal to a negative number? Well, the same negative number or something more negative. So you could end up with something where you have a no solution, okay? Because the square root of something, if it is less than a negative, that will result in an inequality that has no solution, okay? It can be less than a negative, it can be less than or equal to a negative, but a radical cannot be equal to a negative, so the implication is that it can't be more negative either. So if you end up trying to solve a problem and you end up with the square root of blah, 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 blah is less than or equal to -4, stop. There's no need to go forward. There's no need to do any algebra, because you're going to end up with an extraneous solution, or you're going to end up with a series of restrictions or conditions where you don't have any overlap, okay? So the square root of something can't be equal to a negative. It also can't be less than a negative or less than or equal to a negative. If you have that case, it just has no solution.